Hello. Very good morning to everyone. As this is a mass training, so I have muted everyone to avoid the disturbance. If you can able to hear me, just raise your hands. If I'm audible to everyone, just raise your hands. Okay, so I've got enough raised hands, so I guess I'm audible to everyone. I'm Shubham Jain. I have done my civil engineering from VIT, and me and my colleague Mr. Nandeep Gohil, we will be conducting this webinar series. The aim of this webinar series is to walk the attendees through the basic training. And this webinar series is one of the project which has been successfully executed by ACOM India, and we would like to thank Mr. Sumant Gupta and Mr. Piyush Santhalia for sharing and help us to conduct this training session. So the content of the training session will be like, first we will going through the objective, then general overview of MIDAS civil software for the people who are new here, then the introduction, the basic introduction about balanced cantilever bridge, what it is, why it is necessary, and then the live modeling analysis of balanced cantilever bridge. So the objective of this webinar is to model an analysis of balanced cantilever bridge in MIDAS civil. Then to introduce the attendees the fast way of modeling through Wizard, which consists of not only modeling but boundary conditions, static loading, and all construction stages. So by the end of the series, we can say that the attendees will get conversant with FCM Bridge Wizard for modeling of box girder bridge. So this will be the overflow in the upcoming 3 days, which we will be going through. First, we will go through the general overview, which will be today part, general overview and modeling, which consists of MIDAS civil overview, balanced cantilever bridge introduction, project introduction, webinar model introduction, and finally modeling, and then fixed supports, point spring supports, elastic rigs and bearing. Then in the coming days, we will continue with the loading, construction stage, perform analysis and results, which later Nandi will be explaining the other 2 days. Then let's come to the general overview of MIDAS civil software. So many people who are new here, so I just want to introduce MIDAS civil to them. So MIDAS civil is the FES software for analysis and design of bridges. Civil can handle from a simple static to any kind of advanced analysis, and these are some of the worldwide users like Atkins, ACOM, Covis, Scott Wilson, Parson and Brinkhoff. When it comes to application area, it can handle from a simple bridge to any kind of complex bridge like cable stayed bridge, suspension bridge, integral bridge, subway bridge, or any kind of bridges. It is civil can handle from a simple static analysis to advanced analysis such as construction stage analysis, dynamic analysis, 3D tendon and tendon loss, pre-tension girder, dynamic nonlinear analysis. And civil also have wizards or templates for railways like rail track interaction, soil interaction, offshore. So MIDAS Civil is a 3D structure analysis and design software based on finite element method. It is not the special purpose software, it is a general purpose software. It can handle for any kind of project, but the templates and wizard are more design or more towards the bridges. So we can apply MIDAS Civil for bridges and underground structures such as bridges, plant, tunnels, dams. So when it comes to bridges, civil is capable of solving from any simple to complex bridges. So MIDAS civil has a strength in high bridges types such as segmental bridge, which can be balanced cantilever, incremental launching, movable scaffolding, or precast segmental method. Then it can handle from any kind of conventional bridge like culvert, frame, slab bridge, integral bridge to any kind of complex like cable stayed suspension bridge. Also, like as I have told earlier, it has a special wizard or template for railway bridge, underground structure, soil structure integration, offshore, seismic and detailed analysis. So let's come to the introduction of balanced cantilever bridge. What is balanced cantilever bridge, why it is required, and why we have used balanced cantilever bridge, why the ACOM has used for this project. So balanced cantilever construction implies the construction of cantilever segments from a pier in a balanced fashion on each side until the mid-span is reached, and the closure known as stitch or key segment is made with other half-span cantilever construction from the preceding pier. So it's like we have the pier in middle, and on the both side of the pier we start the construction with the segments progressing on both the sides, and then finally it stitch up or stitch with the key segment on the with the FSM on the other side of the bridge. The procedure is as follows. The formwork is suspended from the end of the last segment. The new segment is cast, and when the concrete has developed a predetermined strength, then the section is post tension to the rest of the bridge. So first the new segment is cast. Once it got its strength, then it got post tensioned with the rest of the bridge. So this process keeps on continuous till it meet to the key segment. The same erection process is repeated till the structure is completed. So if we see the view, this is like one of the view of the balanced cantilever bridge where we have the PSC segments, and it is showing in the middle at the center the stitch segment, finally the key segment where the segments from the pier is meeting to the at the center. So I'm not going in deep with the construction stage, as second day Mr. Nandi, he will be explaining construction stage in detail. So here is just for a rough idea. Here I am taking this example for the construction stage. So in stage 1 we have just the pier, and in stage 2 to 13 we have the construction of segments from 1 to 12. So in each stage we have the one segment progressing on both the sides of the pier. So we can see like in stage 1 just pier, stage 2 to 13, 12 segments has been cast on both the sides of pier. Then as we progressed, finally the another segments, and finally it's meeting at the center on at the left and the right end with the another key segment with the FSM1 and FSM2. So free cantilever method, where it is used. So we can say it is generally used in a terrain where obstacles such as river, creeks and roads lie under the bridges, where the accessibility is less. So we need to have some method where we no need to reach the ground, which present difficulty in installing conventional shoring. FCM is generally used for long span bridge, which are typically accompanied with high piers. Since it involves constructing balanced cantilever from a pier, it is often referred to as balanced cantilever bridge. So we can say it as a balanced cantilever bridge or free cantilever method. Then what's the main purpose? The less space required, construction in urban area where temporary shoring would disrupt traffic service below. Then less formwork required, larger span, we can cover the larger span. And more efficient, safe and economical, easy adaptability to curvature, super elevation, useful for odd sizes and single span. So we can see like construction over a working flyover. So without disturbing the traffic, we can go for a balanced cantilever method to construct a flyover over a busy road. Then construction over a railway line. So in balanced cantilever, without disturbing the ongoing traffic or busy roads or the busy railway tracks, we can go on the construction. Then suitable for longer span, it can cover the longer span also. Then consideration for bridge engineer. If we are going for balanced cantilever bridge, then what is the most considerable factor which the bridge engineer need to consider? First is the camber. As we are going for segmental construction, so due to the cantilever action there will be some deformation in each construction stage. Some construction defects may arise, so especially when installing the stitch segment, so we need to take care of the camber. Then pre-stress losses. Pre-stress losses need to be found out for each construction stages. Then finally the overall effect at the final stage. Then creep and shrinkage effect and proper construction sequence. Then let's finally move to our today topic, live modeling of a balanced cantilever bridge. So today we're gonna see a balanced cantilever bridge which has been successfully executed by ACOM India. The project is known as the Jakarta Outer Road Crossing, which has been done for the metro in Indonesia. And the client is PT-MRT Jakarta and the contractor is EWZO. We would like to especially thank Mr. Sumant Gupta, Mr. Piyush Santhalia and Mr. Ravi Sachdeva, who has shared the information with us and helped us to conduct this training session. So this project has been executed by them. And this project has been done using Euro and British code. and for the material CVP FIP code has been used. And for moving load, as there is a special vehicles for this kind of metro in Indonesia, so they have used the user defined vehicle for this model. So this is the model which we will be discussing in this upcoming 3 days for defining properties to analysis. The model have been defined, the model have been modified or simplified to fit the training purposes. So we have modified it a little bit to fit the training purposes. This is a 3-span box girder balanced cantilever bridge having a span length 48 meter, 77 meter and 49.5 meter. With a width of 10.13 meter. As you can see, it is a tapered box bridge which having the tapering from internal piers to the outer piers. And then for moving load and time dependent property, we're gonna use the IRC code. And in structure plan, the internal piers are monolithic, having a diameter of 5 meter, and bridge has a uniform radii of curvature of 182 meter. So this is the box section which we're gonna see today. There are 2 box sections, one at near the internal pier and one is near the mid span. So the web thickness is varying from the mid span to the internal pier from 0.35 to 0.5, and also the height is varying from 2.7 to 4.7. So as we can see in the image here, the height is varying from 2.7 to the near internal pier at up to 4.7. So we will see how we can do the modeling in the MIDAS civil using Wizard, and how easily we can do the tapering also. So today our main focus will be on the self weight of the structure in loading, and then wet concrete, formwork load, and then the pre-stressing. Then in day 2 we will continue with the moving load, response spectrum, temperature, and then further construction stage and all. So type of tendon used for this project, they have used the 19T15 and the 17T15 type of tendon, which is 19 strands of 15 mm dia and 17 strands of 15 mm dia. Total 72 number of tendons are used, and having the pre-stressing of 1395 Newton per mm square. For traffic light length, it is a 10.13 meter width. So as per the carriageway width 8.13 meter, after reducing the crash barrier, we will design it as a 2-lane bridge. So let's move to the model. We can just click on new file. So if we see here, this is we call the ribbon menu. In the ribbon menu, we can see here the structure, node, element. This tab has been designed as we progress in our actual modeling. Like first we define the properties, and then the modeling, then boundary, loading, and finally results. So this tab has been designed as per this only. First node and elements, or the node, all the nodes and element option will get here, like create nodes, create element, delete, converge, or all the options. Then properties, material properties, section properties, time dependent properties and all, and tapering. Then finally boundary. In boundary will get all the boundary options, supports, links, beam and offsets. Then finally loads, all the load options like seismic, temperature, pre-stress, moving load, heat of hydration. Then finally analysis, all analysis option like construction stage, suspension bridge, heat hydration, moving load, and finally results. So all results we can extract from here. So without wasting time, let's just start our today topic, which is the balanced cantilever bridge. So we will start with defining properties. So first we can just go on properties, define material properties, add. So let's just give it name as a superstructure. So as I mentioned, we are using the IRC code for this training purpose. So we can just select from here. So we can just give the name whatever suits us. So I'm just giving the name superstructure and service structure, and then that tendons for tendons. Then finally we can just select the type of, like we are using steel, concrete, or user defined. Then we can just give the user defined also. What is the user defined properties? We can just input manually, or we can just select either concrete. Then for which code we want to define the material properties. So we can just directly select the code, which code suits us. So we select ISRC. Then database, we can directly select it from here, which grade of concrete it is. So for superstructure, we are using the M50. So just select the M50, and then finally apply. So we can see here in outer tab, the superstructure properties has been defined. Then finally we can define the second. So material ID, it's got automatically updated to second. Then I can just name it as a substructure. Then again it will be a concrete type. And for substructure we are taking again ISRC code and then M40. And then finally OK or apply. So the substructure and superstructure has been created. Now we can just give the name as tendon. So for tendon, I will suggest we can just give them manually. We can just go for the user defined option, or we can, for this purpose, we are just selecting the steel type FE. We can just select the IS code from here, ISS, and for this purpose, we are defining the FE 440 and just OK. So like this we can define the multiple material directly from here. Then we can just move toward the section. So in section we can just click on the section from here only, or we can just go close and we can just go from the section here also. Section. So it's just same tab, material, section, thickness. So we are in section tab now. We can just go on add. In add we got the inbuilt database here for various type of section, like the normal section. This is a database for I section, T section, solid rectangular, solid octagon, track, solid track. Then again value section. Value section is for prismatic section, where we just have the properties. We do not want any shape, so we can just directly input the stiffness properties here. Then the SRC, steel reinforced concrete. This is a steel reinforced concrete database. We can just directly select, and as per the self-explanatory image we can just give the inputs. Then the combined section is steel combined section, various type of combined section like channel back to back, angle back to back. So there were the various sections. Then finally PSC section, which we'll be using today for our today topic, PSC section. Then tapered section. Tapered we can directly define it from here. For tapering, it's, let's say if tapering is going from 0 to 10 meter, so we need to define only ith and jth section at 0 meter and 10 meter, and it automatically takes care of the tapering. Then finally composite section, like steel box, steel I, composite T. So let's just move to the PSC section. In PSC section there are again various type like PSC 1 cell, 2 cell. So today our box is PSC 1 cell. Then we can, if it's PSC 3 cell or PSC n cell, we can directly select it from here. And as per this self-explanatory image, just we can give the inputs. So again, whatever the type it is, we can just directly select it from here. So let's just select PSC 1 cell, 2 cell. So if I just move back to the presentation, I'll just show the section again. So this is our section which we're gonna use today. So these are the two sections which we'll be using today. First is near mid-span section and near internal pier. So these both are the single box section. So let's move to the MIDAS civil back. Just a second. So we will just defining PSC 1 cell, 2 cell. So as we can see here, we have seen in the presentation. So as it is curved, when it's going from flange to web at the internal, where the cell it is. So we just need to joint on the joint. We just need to switch on the joint as where it is going the curve. So we are just switching on ZI1 and ZI5. As we can see here, this is the ZI1 joint and this is the ZI5 joint. If I just show the image back. So we can see here, like this is here, it's going, it is not straight. It is going little curved here, and then again it's also at the bottom here, it is little curved, as we can see here. So that's why we need to open that joint, otherwise we'll take it as a rectangular corner. So as per this image, we have to see which suits our requirement best. So this is the joints option as per our sections. Then we can just name it. Let's just name it as a near mid span. So as per this our section, we just need to give the input as per the self-explanatory image. There is a self-explanatory image which explains what is the height, which is the HO1, HO2, then what is BI1, BO1, BO2. As HO1 is the height of the flange, top flange, then HO2 from there to inclined portion up to web. Then HO3 is the web plus bottom flange height. Then HO3 is the bottom flange. So as per this image, we have to just give the inputs. So I'm just giving the input here. HO1 0.25, then HO2 0.25, HO3 2.2, BO1 2.565. So we can see here in image, as per we are giving the input, so the image of that it's creating here. Then BO1 and BO2 is 0, it is totally vertical. Then BO3 2.5, then HI1 0.25, HI2 is again 0.25, HI21 is 0 again, HI3 is 1.7, HI4 is 0.2, HI41 will be 0, HI5 will be 0.3, then BI1 will be 2.15, then 0.75, and BI3 will be 2.15, then BI3 1.95. So again, for web thickness, for shared check, it is automatically calculate the web thickness, so we can just directly give auto. I will just take it 0.25, 2.2. So if we click on show calculation results, we can see the results here. So it automatically calculates all the stiffness values here, its area, movement, and centroid and everything here. Then just OK, and we can just go and click apply. So this is the first section at near mid span, as this is the tapering. So we'll define the another section at the internal pier. So near internal pier. So I'll just quickly define 0.25 HO1, 0.25, 4.2, then 2.565, it will be the same, BO2 0, 2.5, HI1 will be 0.25, HI2 0.25. So HI3, as heights is varying here, HI3 will be 3.4, then HI4 0.2, then HI41 0. So HI5 again it's 0.6, it's varying. Then BI1 it is 2, then 0.75, BI3 is 2. So it automatically asks for save. Then finally BI31 1.8, and we can just click on apply. So same way we will just define the end diaphragm and the internal diaphragm. So let's say internal diaphragm. So 0.25, 0.25, 4.2, 2.565, 0, 2.5. It is 1.6. Then 0.15, 0, 1.2, 0.15, 0, 1.6, BI1 is again 0.75, 0.6, and then apply. Then finally our fourth section, which will be the end diaphragm. So 0.25, 0.25, HO3 is 2.2, 2.565, 0, 2.5, so 0.75, HO2 0.15, HI3 0.9, HI4 0.15, HI41 0, again HI5 0.75, then BI1 0.75, 0.6, 0.75 and 0.6. So this is our end diaphragm, and finally apply. So that's the last section. Again it's the just pier. So for pier we can just directly select solid round. It is a solid round pier of, we can just directly select user of diameter 5 and just OK. So we can directly just like this, we can just create the multiple sections, and then finally we can just do the close. So this is in left, this is called tree menu. In tree menu it gives the complete history of whatever the work we are doing. So as we can see here in works, it's showing that this material and this section we have defined so far. Though this is showing in blue color, it means we have defined it, but we have not used in our modeling. So once we use it in our modeling, it will change into the black color. So now this is the tree menu. Here we got the table option. So any tables like results table or before results table like node table, element table, we can directly obtain from here, like just nodes. So we have not created any nodes, so that's why it's not showing any nodes here. We can just directly go from here, model view. So from here we can obtain the tables, then work, then group. This group is for construction stage, which Nandeep will be explaining. Then finally report for our final word report. Then we just go to the word. Now we'll move to the modeling part. So for modeling part, there is again two way of modeling. One is the conventional way of modeling. We create nodes, then elements, then join them. So this is one of the conventional way. So instead of this, we're gonna discuss today through the wizard for the quick modeling to save the time. So for the, if you go to this node element, this is for conventional way. We can just go and create nodes, then create elements. So for this is the one of the way of modeling. Then another way is through structure. In a structure we have the various wizards like cable state wizard, suspension bridge wizard, free cantilever wizard, incremental launching wizard, movable scaffolding. So directly we can model fast from wizard also. So wizard take care of everything for modeling, boundary, construction stage, everything we can take care of wizard. So we just go FCM bridge wizard. So we can directly click FCM bridge. So if we open here, we can see here there's a self-explanatory image here as it's showing at the left. First as fully staging method FSM starts, then finally K1, which is the segment one, which is a key segment which is meeting the segments coming from the pier. Then this is the zone 1 which starts from the pier. As we can see here, these are the numbering 1, 2, 3. So it starts from the pier side as the construction stage, balance cantilever. Then finally pier table, then zone 2, K2, and as it's symmetric, same on the right hand side. So we can choose also either it's symmetric or asymmetric. We can give the input as per that. So we have to just give the normal data input here. So it automatically creates like if just the material, whatever the material section we have defined, we can just select here. So material for gutter, so it will be superstructure. Then material for pier, it will be substructure. Then number of piers, as in our case, it is 2 piers. So if I just show the presentation again. So this is our case. So we have the internal 2 pier and then finally 2 pier at the ends. So we are talking about here the internal pier. So internal we have 2 piers. So we will be taking care of this 2 piers. So number of piers 2. Again method, we can select the method either it cast in or pre-segment method. So it is a cast in method, so we can just select cast in method. Then stage duration. So stage duration they have taken like 13 days for each construction stage. Then finally what is the pier table. So we can define the pier table here. So where my diaphragm is covering, where's my left segment and then right segment. If it's the diaphragm, we can directly give the pier table. And if we have the diaphragm over a just small portion, let's say B, so we can just go for the advanced option. Here we can define. So there is an option called pier table type. Either there is just one diaphragm, single diaphragm, or the double diaphragm. We can directly define it from here. If it's single diaphragm, so T1 is the segment length for your left segment. From the diaphragm, what is the length of my left segment? So that we have to give. So T1 to T1 here it's the 2.5. Then T2 is my diaphragm length. What is my diaphragm length? Which is the 5 meter diaphragm. Then T3 again it's the 2.5, which is the segment right to my diaphragm. And then B, the width of the diaphragm, it will be again 5 meter. And we can just, I will just delete this, or we can just define again just 2.5. 2.5, 5. Again 2.5 and then finally 5 and then define. So our PT1 has been defined with the diaphragm of 5 meter. Then same way with P2, the same thing we have to repeat, 2.5, 5, 2.5 and again 5 and define. So our for two piers, the diaphragm has been defined above the pier table. Then just do OK. Then same way, just we have to input what is my key segment length. So what is K1 is the at the left, and then K2 is at the center. So K1, the segment length is all 2 meter each. So we'll just add the 2 meter. So if K1 is 2 meter for left and right ends, and for the center segment length is 3 meter. So key segment is 3 meter. Then we have to give the input. What is my pier height and what is my pier center to center distance? As we have only one pier, so center to center distance will be 0, and pier height is over 19 meter. Then we have to input this FSM at left, which is here at left, and then FSM at right. As it is symmetric, so we can just give the FSM at left, and then finally we can copy the same in FSM right. Okay, so let's just give the FSM at left. So as per whatever the division has been done in the model, so we are giving the input as per that only. So it is first 2 at 2.6. 2 at 0.6 means the two segments of 0.6 length each. Then 1.375. So this input is depend upon as whatever the structure it is. So how we have how the structure is, how we are modeling. So this input we have to give the as per that. Then 1.375. Then finally 3. And then 3. So if it's same as I said, we can just copy and paste in the FSM right. If it's different, we can again give the input for a symmetric one also. Let's just give the input 2 at 0.6. Then 1.375. Then 3. And then 4.5. Then we have to give the input zone 1 and zone 2. So this is like for construction stage, which gonna be zone 1 and zone 2, which have the segments constructed from the pier on both the sides. So zone 1, zone 2, if it's symmetric, again we can just copy. If it's asymmetric, we can just give the input for both. So zone 1, it's just 4 segments of 3 meter each, so 4 at 3. Then comma 5 segments of 4 meter each, so 5 at 4. So if it's same as I said, you can just go copy and we can just paste it here. So 4 at 3 and sorry, it's just a 5 at 4 meter each. So we can select directly. So we have defined till far the material, our pier section, our whole segment length. As we have seen, this is the curved bridge, so it has a uniform curvature. So it has a uniform curvature. For that we can just directly select the radius. So it has a uniform curvature of 182 meters. So we can directly give 182 meter here, radii curvature of 182 meter, and it has a concave type, so we can just select the concave type. So as we can see here, so wizard is for generalized kind of structure. So here we can generate a uniform kind of section having the uniform radii and all, and here the section generate from, like say, support to the pier. We can consider the tapering and everything here also, but if we have some section, some different section at the middle or something, so we can generate the segment length as per that, and later we can do the modification. At that length we can then change the section property and all. So like we can just generate our initial model from the wizard, and then later we can do the modification and finally come up to our final model. Then we can just move to the section. So here we have given the stage duration. So it is each construction stage. So it's take the total, it's take the constant duration for each construction stage. If we are taking the like depending on the segment, how much in zone 1 segment we have defined, as per that it take the construction stage. If we have defined the 10 segments, it will take as the 10 or to 11 construction stage. Of each construction stage duration 13. So it's take the constant construction stage duration, but the construction stage duration can be varying. So we can modify the construction stage duration later on also. So here it reduces the time of defining the groups and then activate, deactivate in each construction stage. As in construction stage 1, segment 1 will be activating. In construction stage 2, segment 2 will be activating. So this time it get reduced. So later we can just do the modification. Then we can define the member age here also. So what is my member age? So like I'm not going in deep in construction stage, as tomorrow or Mr. Nandip, he will be explaining in detail. So here this is the age of the concrete for key segment pier table at the activation of that construction stage. So let's say this is 3, Period table. So we are defining just the some random, this is the day duration, or we can say take it as a 0 itself, which has been taken in actual model, and OK. Then we can just move to the section part. So here section, again there are two types. We can just directly give the input here for section if it is a constant section, or we can just go to the cell 2 or the type 2 type. In type 2 we can just select the section here which we have defined earlier. So for center it is a near mid span, then at peer table near internal peer, then this diaphragm, this is for internal diaphragm, so we can just directly say internal diaphragm. So we can just directly select cell update display, so it display here also what is my near mid span section, what is my near internal peer section. Then formwork tabular load, as it automatically taking care of construction stage, so it automatically deactivate and activate formwork tabular load as per the construction stages. So it automatically just we have to give the input how much construction stage, how much formwork tabular load we are considering, and what eccentricity respective to the segments. So we are taking as the formwork tabular load as the 10 kilonewton at the 10 kilonewton at the eccentricity of 2.5 meter. Then for wet concrete load, it automatically calculates the wet concrete load as per our the material inputs. So we can just directly do tick on from here, include wet concrete load. And finally, if we want to give the input for tendons, we can directly give the input from tendon here also, or we can give the manually input for tendon later also. So I will go for the manual input of tendon that I will be explaining after creating the model. So after giving this input, we can just go for OK. Just member age, just let's here 1. Okay. Okay, just one more thing here. When we are defining section here, just we have to take care of the offset also. This is the offset as we are doing the load line element modeling, so we have to take care of the offset as the whatever the loads we are defining with respect to the top surface. So we have to take the offset as a center top, and OK. Okay, I'll just do the little this modification. Just the offset I am taking this as a center top. So we can see this red rectangular bar, this show the offset here. Earlier it was center. So what it means, the offset is this blue one. This here is the our node position. So as we are defining loading and everything on the surface, so we have to take it as a center top. So we are shifting this offset as a center top, and OK. Close, and then finally OK. Just a second, I'll just go again in the FCM with wizard. So again here peer section, it will be peer, then section, and finally OK. So our model has been created. So we can see here how much time it saves. So it's created the whole model with the peer and everything. So it has created the supports also here, supports, elastic links where is required node local access for the curved bridge. So it automatically chooses. If you see here in work menu, earlier we have just defined the material and section only. But now everything, if we just go in the front view, so the tapering and everything it do automatically calculates as per we have the inputted the section at the peer and at the center. It do automatically calculate the tapering and everything, and it do the complete modeling as per whatever the inputs we have given. So our model is ready. So like this, what I means to is, so wizard we can use for the quick modeling, and later if also we have some modification, like if let's say this element, if I just select, this is for selection option here, this is select. So if this element is varying or something, it's a different at the end or something, so we can just directly change the section. We can just directly do drag and drop and assign this section. Now if it's say in wizard, we don't have the inputs for defining the end diaphragms. Now these two segments we have considered it in the FSM, but these two are the end diaphragms. So what we can do, we can just select these two section and just assign the end diaphragm property. So we can just do drag and drop. So now these two section end diaphragm has been defined, assigned to this two section. Now same way this right hand side also, this is the end diaphragm. So we can just select this two section and just assign the end diaphragm section property. So like this we can do the modification after creating the complete model. Now again, this is the two key segment has been created. This is the one key segment, so I'm just gonna merge it. So there are some modification which we can do after just creating the complete model. So I will just merge these two sections. I will go to the node element and just merge element. Then in merge element, what is the type? It's frame type. So force merge and just click on this box, and no need to select even. Just click on first section. I'll just zoom it to have a clear understanding. Just click on this box, just click on first section and then the second section. So finally we can see here this both section are got merged. Then finally here we have the key segment. So if I just go to the element number, from here we can give the element number also. So if we see here this two section, these are the one key segment. Again we can just create a one key segment from the wizard, which should have a length smaller than the previous segment, and then the segment after it. So the sixth, which is the key element, which is the key segment, it should have a length smaller than fifth and the seventh element according to the wizard. But here in this, as per this model, the key segment is bigger than that. So what we have do, we have included the half of that part in the left segment, and then we're just gonna merge it. So just we're gonna merge this both segments. So same way we're gonna do it right. So 53, 54. So we're just gonna merge it. So this section has been merged. So we can, like this, we can do just modification at the end. So we have to give the inputs suiting our modification and everything as per in the wizard. So now our model has been done. So substructure, Mr. Nandip, he will be explaining tomorrow. And then I will just go for the pre-stressing. For pre-stressing, we can just go into the load. For before pre-stressing, as we need to select the element in which the pre-stressing is going on, so I will just give the renumbering for that. So what I will do, I will just select the elements, the top of our beam, and I'll just give the renumbering. So because as we have done the merge of some elements, so it's, some element now after 5 like this directly 7 is coming. So I will just do the renumbering, so it will come in the continuous manner. So numbering, renumbering, node and element by selection, and then apply. So now I can see here it's coming in continuous manner. Now what we can do, we can just directly go close it. We can go for the pre-stressing. So again, we can just directly go to the load, temperature pre-stress, and then tendon property. So if I just show here, just pre-stressing, this is our pre-stressing. This is a type of tendon used, like 19T15 and 17T15, total 72 number, and then the pre-stressing force of 1395. So here, as it will take time, so we are not gonna input all the 72 tendons. We will just gonna show you some 2 or 3 tendons. Then finally we have the pre-done model where we have with total of 72 tendons. So then we will see that one. So we will just go to the tendons. So again it will ask you for saving, we just save it later. So we can just, so again defining pre-stress, it's the 3-step process. First tendon property, tendon profile, and then finally tendon pre-stress. So we can just go to the tendon property, we can define the tendon here. So we can give whatever the name we want to give, or we can just directly give 19T15. So material again is tendon. Then total tendon area, we can just directly select what is the diameter. So it's a 15 diameter. We can just say it as a 15, or we can directly give the after calculating, we can directly give the input here also. So I'm taking like say 15.2, and number of strength is 19. It's okay. Then duct diameter 0.1. So the total tendon area, duct diameter, then relaxation coefficient either as a Margio, IRC, European. So as we are using IRC, so I'm taking IRC 112. Then either normal, low, so we are taking normal. Then ultimate strength and yield strength. So ultimate strength is again same 1.8 into 10⁻⁶, and this 1.5 10⁻⁶. Then I'm just giving OK. Then add. Same way we can define the 17 T15. internal post tension, then tendon, total tendon area, so 15.2, again number of strands 17, okay, then duct diameter 0.1, and then for IRC 112 and normal, then ultimate strength, yield strength, curvature friction, over friction factor, I'm taking this the same, and then finally okay and close. Then we have to go to the tendon profile. For tendon profile, we can directly just can give the input of the coordinates here. So if I just go to the tendon profile, add, so here we can just directly give the whatever the name it is, let's say T1. So tendon property, again which property, we have defined the two properties, so for which property it is, so it is 19T15, so 19T15. Then assign elements, so the first tendon it will be going from the element 1 to 19. So we can see here the element number, it is going like from 1 to 19. So we can directly give the number here, let's say 1 to 19. Then again 2D or 3D, we can input in the terms of 2D, X, Y, and then XZ coordinate, or either in terms of 3D. So we can just directly go for 3D. So I have the predefined coordinates which I have taken from the model which has been done by the ACOM. So I'm just importing that coordinates. So this is the coordinates I'm just copying. So we can just have from the Excel sheet, we can have some predefined tendon coordinates from the Excel sheet, or we can just copy it and we can just paste it here. So whatever we have the coordinates, we can just directly paste it here. Then we have to tell profile insertion point, as we are going from 1 to 19 elements, so profile insertion point, the element number will be 1. So in element 1 we are inserting the tendon. We can also select either at ith end of the first element or at the zth end of the start end or the end of the first element. Then we can directly give the OK. So our first tendon has been created. So like this, if it is going in, like if it, let's say this is the tendon at the, if I just open it, this is at the -220 meter, which is means at the left from the center line, from the center of the line, which we have selected this, which is highlighted by the red color. So if we have the same tendon at the right side, we can just mark it as a copy. We can just select this tendon and we can just copy and move. So we can just do the copy of it. So equal distance we can just directly give, and the current assigned element, because it's going to be assigned to the same elements, then 0, comma. So what is the total distance? So this is the total distance. This is the cumulative distance dy from first tendon to the last tendon. So this is again 2030. Then we can just do the OK. So the same has been copied from the left to the right hand side also. So no need to define the again and again. So same way we can just go define the multiple tendons. So tomorrow Mr. Nandip, he will be explaining the construction stage analysis and the model with the inputting all tendons with 72 tendons and with the substructure. So we will just stop here with the tendon pre-stress as we are running out of time. So we will just define the tendon pre-stress. For that, for tendon pre-stressing, first we need to define the load case. So let's just say pre-stress. So pre-stress, again the type, pre-stress type, and just add and close. So we can again just select the load case name as a pre-stress. Then what is the tendon it is? So all tendons at jacking with the stress of let's say both end, and we can change the unit anytime from here. So we are working in kilonewton meter, so we can just select it here. So we are just giving the inputs in the Newton mm for the pre-stressing. So Newton mm, so it is 1395 Newton per mm square. So we can just directly give 135 Newton per mm square. So 1395. And grouting after 0 stage, as we are doing the grouting is first stage, and then add. So like this we can give the pre-stress. So our pre-stressing has been done. So first tendon property, tendon profile, tendon pre-stress. As it's gonna take much time for inputting 72 tendons, so I'm just showing for how we can input just the 2 tendons, and same way we can go for the another 70 tendons. So thank you everyone for attending the webinar, and I hope this is helpful for everyone. And in the another 2 webinar, we will complete this model with the substructure, construction stage, moving load, and we'll see how we can do it more easily and quickly. So thank you everyone. If anyone has any question, you can write us at techsupport@midasit.com, or you can just write right now here in the question and answer session. Thank you.